I'll start with some of the introductions. I believe there's a sign-up sheet circulating that TAP likes to keep track of, so please do that. My guess is there's about it's sort of a 10 to 40% completion rate on that sign-up sheet, so we can try and get closer to the 40% this time. I guess that would be good. It's not clear that, yeah, anyway, I save my thoughts on that for later. So part of the reason that sheet is going around is because Fred has been visiting us this whole week as part of a TAP lectureship as part of the Planet Formation Initiative. So it's been great to have Fred around all week, and he's around for one more day tomorrow, and we'll try and his schedule is already filling up for tomorrow, but you can look on the link to see if there's any more slots available. So I'll try and keep this brief given all of Fred's accomplishments, but Fred got his PhD in Berkeley. He then went to a PhD postdoc at the CFA and then became a faculty member at the University of Michigan. There he's now a named professor of physics as well as a director of the relatively new Lineweaver Center for Theoretical Astrophysics. So really look forward to seeing how that develops under Fred's leadership. So Fred's research has spanned really a wide range of topics, a lot of work in many aspects of star and planet formation, stellar evolution, and all the way to cosmology, which is, I think, what he talked about in his last colloquium here several years ago. So Fred's work has been widely recognized, including with the Trumpler Award and the Warner Prize, as well as many teaching distinctions from the University of Michigan. So already this week, Fred has delivered a couple of excellent talks on both giant planet formation and the mass function of the Kepler exoplanet sample. Today, he's going to talk to us about the environmental effects of star clusters on planet formation. And we welcome Fred.
Okay, well, thank you, Andrew, and thank you all of you for coming and bearing with me for yet a third talk this week. So appreciate that. And thanks for inviting me to your fine institution. I always had a good time in Tucson, and I should come more often. So thank you so much. Let me begin by saying that I'm going to steal work freely from a whole bunch of different papers. These are the main collaborators from which I'm going to steal. There's a few others. Some of you are in the audience, but let's get right into it. So I begin by working on the star formation problem. And when we were doing the star formation problem, we were studying one star at a time. We're just studying the 4 stages of star formation back in the 80s, as you see in the middle slide. Now, after we sort of got to a stopping place in that, we wanted to ask 2 more questions. One is, how do planets form on the smaller size? And then we also realized, because the observers kept telling us that, hey, stars form in clusters, which leads to the question, how does the cluster environment affect the star formation problem? So what I'm going to do today is I'm going to tell you how the cluster environment affects the planet formation problem. And you'll see what I mean by that in a minute. So the 2 questions I want to ask are the following, and this is sort of a coupled problem. The big problem, the main thing I'm talking about today, is how is it that clusters affect forming planetary systems within them? But if you look around, it turns out we live in a planetary system, right? And it's a natural question to ask, what, if anything, can we say about the birth environment of our own solar system? Now, it's kind of a tough question, because the scene of the crime was 4.5 billion years ago. But can we say anything? I also want to say that one thing, I did a bunch of work on this in the first decade of the century, and this culminated in a review article, which is written about in 2010. I've done quite a bit of follow-up work. A lot of what I'm going to tell you today is the basic story, and many of the details I will leave at the bibliography at the end. And I should also say you should feel free to ask questions, and I'll do my best. Okay, so let's begin with some basic timescales. The time it takes for a star to form is order of magnitude 1/10 of a million years. And what I mean by that is that the time it takes for the collapse to happen and most of the mass to go from the core onto the star is about 10 to the 5 years. That means m dot, the mass accretion rate, is 10 to the -5 solar masses per year. That's the typical number for forming a solar type star. In contrast, if we look at the embedded phase, we see that clusters remain embedded for 3 to 10 million years. Laurie Allen has told us that, so we believe her. She's not the only one, but we believe her. And we also look at circumstellar disks. Circumstellar disk lifetimes are measured by Jesus Hernandez. So Jesus told us how long they live. And they live 3 to 10 million years. So we have to believe them as well. And then if you look at the theories for giant planet formation, it turns out it takes 3 to 10 million years to make a giant planet like Jupiter. So if you look at those three timescales, they look kind of sort of the same. And that's why it matters. Embedded clusters, circumstellar disk lifetimes, and planet formation all take place on timescales measured in millions of years. And that's why there's this commensurability that they might affect each other. In contrast, other things you might care about happen on longer timescales. Terrestrial planet formation might take place on an order of magnitude longer timescale. The late great heavy bombardment that sculpted Earth was hundreds of millions of years later. And open clusters, the 10% of the clusters that are big and bad enough to be an open cluster can live for an order of magnitude or more longer. So these are the timescales we should keep in mind. Now, I'm going to give you a very simple collection of results here. And one of the things that I'm going to need to do is to say what I mean by a cluster, okay? Now, there's a whole bunch of clusters with a whole bunch of different sizes. There's a classic paper by Charlie Latta, who used to be here, and Liz Latta, who I don't think used to be here, and their collaborators, and they have compiled a distribution of all the clusters in the solar neighborhood. And long story short is that the number of clusters as a function of membership size n goes like 1 over n squared. So the probability that a star will be born in a cluster of size n goes like n times 1 over n squared, which is 1 over n. So the cumulative probability goes like log n. And what this means, if you just don't worry about the algebra, is that every decade in cluster size matters. Now, here's where there's a little bit of a problem I want to come clean on. The sample that I'm using here only goes out to the solar neighborhood, which means it doesn't sample the highest end of cluster membership sizes because you got to go farther away to get to the big ones. If you look in external galaxies like Rupali Chander and her friends do, you find exactly the same form at the high mass cluster end in external galaxies. I'm going to assume that we can match those two things up. The functional forms are the same. We don't actually know for sure that the normalization is the same. I'm going to assume it is. You can adjust everything I say when I give you a probability accordingly, but I want to come clean that that's what we're going to assume. So we have a cluster sample and we know how many times I get such and such a cluster, and I will just use this as an underlying probability distribution whenever I need to calculate a probability for the next 3 hours of this talk, okay? I get 3 hours, right? Okay, so when we look at clusters, we can kind of divide what they do into 3 camps. One of the things they obviously do is they support dynamical interactions. Another thing they do is they provide strong radiation fields in the UV and the X-ray, for example. And the other thing they can do is they can provide extra particles. These extra particles can take the form of cosmic rays, which can lead to heating and ionization and change chemistry. They can also be radioactive and lead to enrichment of radioactive species and heating and such. So a quiz for you guys. Which of these 3 matters the most? Why is no one raising their hand? I will reveal the answer in due time. Before I do that, I want to lay another thought on you, and that is this. Why am I talking about planet formation instead of star formation? And the answer is that clusters have more of an effect on the planet formation problem than on the star formation problem. And let me say more explicitly what I mean by that. When we look at clusters, we see subunits in them, the things Phil Myers calls kernels, but these are little molecular cloud cores within the larger forming cluster. But they're moving subsonically. They're moving at 1/10 of a kilometer per second. And we just saw that the collapse time for making a star is 1/10 of a million years. So if you do a little bit of math, you take it 1/10 of a kilometer per second, times a tenth of a million years, you get 100th of a parsec. Now, the cores are separated by 0.24 parsecs or so, given on typical separations. So the point is that during the time that a star is doing its collapse thing, the time that we would have called it a protostar back when we were young, during that time, it's only moving a tiny fraction of the distance to the next protostar. The number of dynamical interactions just doesn't matter. Now, the cluster environment could play a role in the earlier phase in saying how it decides to make those cores, but that's not the problem I'm doing. Once it's made the cores, the cluster environment has nothing to do with the dynamics of the actual collapse because the collapse happens on a much faster time scale than the interaction can. However, as you saw from that commensurability of time scales on the previous slide or two, the cluster can affect the planet formation problem. Okay, so let's jump right into results. What I'm going to show you first is a collection of n-body results. These were done by a grad student long ago named Eva Proskow. So these are basically just n-body simulations of the cluster where we gin up the initial conditions to be as much like the Lotta sample, the observational sample, as possible. So that's just sort of standard n-body physics. I'm not going to belabor the details of it because everybody has heard these things before. There's two things I want you to emphasize that might be different. Because the cores or kernels are moving subsonically at the beginning before the stars form, the initial conditions for the clusters are a little bit different than some simulations use. In other words, the cores are moving slowly and then they make a star, and then the star literally goes ballistic as it starts to enter a ballistic trajectory. But that means it has a cold start. It's not moving, the star is not moving at the virial velocity when it starts, it's moving subvarially and it will collapse further in. So that not everybody does that when they do n-body simulations. So the other thing that you have to do is that because we want to mine the results for statistical results, we have to do more than one simulation of the same morally equivalent cluster in order to get enough statistics to say what the results are. So we do many, many realizations of the same cluster in a way to get the statistics. So the first result I want to show you is this. You can ask, what is the distribution of closest approaches that a star in an embedded cluster will see? And it's a simple power law. If it were just the geometric cross-section, the coefficient little gamma would be 2. As you see from the table, the gamma values for various cases are somewhere between 1 and 2, a little bit less than 2. That's because of gravitational focusing, which you expect. So that's not a revolution. The coefficient in front tells you how often the interactions happen. So one of my points that I'd like to leave you with today is that whenever you ask a question, what does a cluster do to a star? Or what does a cluster do to a planet? Or what does a cluster do to a disk? The answer is never an answer. It's a distribution of answers, okay? So the answer of how often do you have interactions, you get a power law distribution of closest approaches, okay? So one lesson is that you should always answer in terms of distributions, not numbers. Now, I'm going to violate that, okay? You can say, what's the expectation value for the closest approach that a star in a cluster will have during the 10 million years it kind of hangs out as an embedded cluster? And the answer is order of magnitude 1,000 AU. So what that means is that on average, not the full distribution, but on an average expectation sense, every star is expected to see a closest approach of about 1,000 AU. It's very rare to be a lot closer than that, and it's very rare to get away with not being that close, right? So the million-dollar question is, what does 1,000 AU approach do? Does Jupiter at 5 AU care? No, it does not. What this will do is 1,000 AU closest approach will truncate disks down to about 1/3 of that value. 1/3 of 1,000 is about 300. 333, but 300, which means you're going to truncate disks at a scale of about 300 AU. That's the typical thing that the dynamical interaction does to disks. Now, we all know from ALMA and other sources that disks are 100 AU. We actually predicted that in the 80s, and then it's verified in spades in ALMA. Some are a little bigger, but 100 AU is, it turns out, less than 300 AU. So what that means is that the truncation is a modest effect, something you have to take into account, but it's not driving the show. And keep in mind this 300 AU number because it will come up later, okay? So let's look at other kinds of dynamical interactions. Once you've made a planetary system, you could imagine that the interactions between binaries and single stars and solar systems will lead to all kinds of interesting interactions. Now, to do this problem, it's kind of a mess because if you just think about it, suppose you have a 4-planet system like the giant planets of our solar system, you have to specify, to start a simulation, you have to specify the 6 space variables of all 6 or all 4 planets. Then you have to specify the eccentricity and the masses and the semi-major axis of the binary you're interacting with. And then you have to specify all the parameters that describe the interaction, the velocity at infinity and the impact parameter and so on. So there's a whole bunch of variables depending on which system you're doing. For just a 1 planet system, you have 13 parameters, which means the usual way to do this is to Monte Carlo it. So what you do is you Monte Carlo sample this enormous parameter space, but you do it subject to some choice of distributions. And what you usually do, and what I will show you results for, is to sample the IMF and sample the binary period distribution and eccentricity distribution. And then I'll do it for a particular velocity distribution, namely something like a kilometer per second, which is the velocity distribution in a cluster. And then you do bazillions of these for particular cases. And here's the typical case, which means it's the most interesting one. So here we have a binary interacting with the Earth and the Sun, just to show you what happens. And you see you get this 9,000-year resonant interaction where the binary comes in, it steals Earth, one of the members of the binary steals Earth from the Sun. It orbits around for thousands of years, gives the Earth back to the Sun, who then palms it off on the other member of the pair, who then leaves the dance with the Earth in tow. So this is kind of cool. The chances of this happening before life dies on Earth is about 1 part in 10 million. It's about the chances of you winning the lottery. This is kind of nice because it saves life on Earth. Otherwise, it's just a curiosity. Now, this is just a curiosity because I think it was kind of cool. But what you really can do is you can look at interactions of binaries interacting with the 4 giant planets of the solar system and see how much they change the orbital elements. And you see that each simulation will lead to a new set of orbital elements. The size of the symbols is given by the size of the binary that interacts with it. And you see that in the semi-major axis eccentricity plane, the results of these scattering interactions is to not change the semi-major axis all that much, but you get this explosion of orbital elements to high eccentricity. Now, this is just what happens. What you care about quantitatively is a cross-section. So, from all of these simulations, you can mine the results and calculate a cross-section, which is the effective area that the solar system in question subtends for any particular dynamical interaction. So what I'm plotting here in the 4 panels are the cross-section for increasing the eccentricity from 0 up to whatever eccentricity I'm plotting for the 4 giant planets, which are the 4 curves I'm showing for 4 different stellar masses. And what's cool is that you can fit all of these curves with a single fitting formula that works pretty well. And at the end point where you've increased the eccentricity from 0 to 1, that corresponds to ejection of a planet. So we have a net cross-section for ejecting planets. Since we know the cluster dynamics, we know its density and its lifetime, and n sigma v gives you the interaction rate, I can fold this all together and predict for you the expectation value for the number of planets that are ejected in a cluster during its 10 million year or so lifetime. And the answer is 2. In other words, in a cluster, you expect a couple of planets to be liberated, assuming they have something like the giant planet's kind of orbit. If they're much further out, then it would be higher. But for that case, you expect a few planets to be ejected. But this is relatively rare. It doesn't explain the large numbers of freely floating planets that we might see. Some people believe those results more than others, and I will not comment on them further, other than that there are lots of observations showing there could be freely floating planets. Their origin probably lies elsewhere, as in not from ejections from passing stars. Now, you can take this one step further. I had a, well, she's now a professor, she was a grad student at the time, do 1 billion simulations. No, she only did millions of simulations, excuse me. And Gangji Li did this, and she covered the whole phase space. So you can find a fitting formula for the cross-section for any planet with a semi-major axis A in an environment with a velocity dispersion VB around a star of mass m star, and you can find the cross-section for increasing the eccentricity from 0 up to a value E. And these fitting formula for both binary stars in the top and single stars in the next line actually work really well. The Monte Carlo sampling error is only 1%. The degree to which these things are self-similar enough to have a single fitting formula is a little bit worse, it's like the 10%. But at the 10% level, you have a cross-section that works over this enormous parameter space. And the calculation is already done for you. And this is a way to allow you to figure out what kind of scattering interactions might happen in clusters in general, or in the field for that matter, because it goes up to larger velocity dispersions. Another thing that you might ask about is, what about capture of rocks? If you make a solar system in a cluster environment, the planet formation process will send out lots of rocks. Now, the reason why you care about rocks is that some of those rocks could be infected with life. In fact, our solar system was born in a cluster probably, and our solar system, we think, has life. Now, if that life happens soon enough, some of the ejected rocks from the Earth's surface would be sent to other members of the solar birth cluster, thereby providing it with rock-bearing lives. So what's the likelihood of this happening? Well, it turns out that solar systems eject so many rocks that the story is exactly like daycare. When you take your kid to daycare, every kid shares germs with every other kid over and over and over again. So if you make a solar system in a cluster, every solar system shares rocks with every other solar system many, many, many times. Now, turns out I don't know anything about life. Those of you who know me will verify this. And so I don't know how many life-bearing rocks we're talking about. But what I can tell you dynamically is that there's lots of rocks that are being shared among cluster members. Now, there's one other result I want to advertise a little bit. I had another student named Kevin Napier, who during COVID did 1 billion simulations of rock capture. And instead of just doing a Monte Carlo where you sample the velocity from some dispersion, he did the cross-section for each individual velocity value, which is sort of an order of magnitude more computing. And that's why this couldn't be done until 2020, 2021, because computers weren't fast enough. But what you get then is a cross-section for rock capture as a function of the velocity at infinity. With that velocity-dependent cross-section, you can then convolve it with any distribution of velocities and give you the cross-section for capture that you care about. The other thing that's kind of interesting, which I won't go into, is you can derive an analytic treatment that gives you the cross-section. So the red line is my analytic approximation. The dots are the result of 1 billion simulations that Kevin did. We had a lot of time during COVID, so we could put all these pieces together, and we have a pretty good description of what happens. So I've given you a flavor of what are the dynamical interactions that happen within a cluster. And what you should take away from this discussion so far is that the effects are modest, okay? Clusters will eject a few planets. They will disrupt some orbits and give them some eccentricity, but it's not completely dominating or completely sculpting the properties of the solar systems. So let's look at radiation. So I'm switching gears to point number 2 now. Radiation has basically one important effect. It evaporates disks. So the idea is that cluster environments provide a enhanced radiation field, and those radiation fields can evaporate gas off disks, thereby truncating them. Remember, the dynamical interactions truncate disks down to 300 AU. Let's see what the evaporation does. Now, you can do this with both FUV and EUV. Since this is a mystery story, I will tell you the FUV rather is much more important than the EUV, and I'll demonstrate that for you shortly. And then to give away the story, with a typical FUV flux of 3000, and I'll tell you what that means in a minute, you truncate a typical disk down to 36 AU. So 36 is less than 300. 36 is small enough it's starting to matter. It's kind of close to Neptune's orbit, which is where our disk is truncated, as in our solar nebula disk is truncated. So evaporation seems to be more important. So let's see how that works. So the first thing you need to do is say, well, what's the typical distribution of FUV flux in a cluster? To do this, you have to take 3 distributions. You have to sample the cluster distribution. Then within each size of cluster, you have to sample the IMF. And then within each one of those realizations, you have to sample all the positions inside the cluster and calculate the flux from the massive stars that gives you the FUV. And then you do this over and over and over again until you build up a distribution. You get an almost Gaussian distribution like the one I showed you. And it peaks at something like 3000 in G units. G units are the interstellar FUV value. So that means that the clusters typically, even though there's a distribution, typically give you 3000 times more flux than the background galaxy. And the value where G is 1 is 1.6 times 10 to the minus 3 in CGS units, for those of you who like CGS units, okay? So this is what you typically get. You get thousands of G units worth of FUV. What does it do? Well, it leads to evaporation. So I'm going to build for you an evaporation model. So the basic idea is you have to integrate the fluid equations from the disk surface through the sonic point and outward. This is sort of a straightforward calculation, except you need to know the temperature as a function of density and column density at every point in the flow. But in order to do that, you have to know how much is heated from the FUV coming in from the outside. And in order to do that, you have to keep track of all the chemistry, because different species come in and out of existence at different column densities and different densities, and they lead to different amounts of cooling, which give you a different temperature. So if you plot the temperature curves as a function of column density for different volume densities, you see you get these messy, complicated curves. And the worry is that you might have to get complicated results. The good news is that when you do the calculation, most of those things average out. So the fluid fields shown in this plot are more or less smooth curves. There's little wiggles there you can barely see, which are the imprint of this complicated chemistry that I briefly described on the previous slide. And from this, we can build an evaporation model. And I can present the results of the evaporation model thusly. For a given radiation field, G, I can tell you the evaporation time as a function of radius. So for a radiation field of 300, ain't nothing happened. For a radiation field of 3000, in 10 million years, I evaporate down to 36 AU, just like I mentioned earlier. For a radiation field of 30,000, which is 10 times larger, I can evaporate down to about 15 AU in 10 million years. So you notice this, that evaporation can matter. It can affect Neptune formation because it works at sort of the 30 AU level. Jupiter is always safe. Even if you have 10 times more radiation than average, you still don't evaporate anything near the Jupiter formation plates. So it's hard to compromise Jupiter formation, even in the most extreme radiation environments. Now, we can do the same thing for EUV. So I can build up EUV distributions. People use different units for that, just CGS units. Here's the distribution. For the EUV evaporation, it's actually much simpler. because you don't have to do all this heating and cooling. So I can calculate the corresponding curves for different values of the EUV radiation. The one marked with the green dot, which is the 10 to the 12 in CGS units, that's the one that's at the peak of the distribution. And you see that truncates disks down to 300 AU. So to summarize so far, dynamical interactions typically give you a truncation of disks at 300 AU. FUV radiation typically gives you an evaporation down to 30 or 36 AU, and EUV radiation gives you truncation at 300 AU. So clearly EUV evaporation is what wins. It's also true that as I go from solar type stars down to small stars, evaporation becomes more important. So it's possible for evaporation to compromise giant planet formation around M stars. And it's also the case that as stars' external radiation fields evaporate disks from the outside, accretion is draining the material from the inside. So the disk lifetimes is given by the intersection of those. For typical values for the models I've shown you, the typical lifetime, the typical upper limit on the lifetime from this is 8 million years, which is nicely commensurate with the 3 to 10 million years that we began the discussion with. So at least there's a consistency check here. You can look at X-rays. I won't say much about that because I'm going to run out of time. X-rays don't do as much as EUV and FUV, but it is true that the background X-ray field will dominate that of the central star as long as you're at about 30 AU or so. But the main takeaway from this part of the talk is that the radiation effects are actually much more important for sculpting forming solar systems than the dynamical effects. That might not have been clear from before we did the calculation, but that's the bottom line that we're seeing. So let me briefly talk about some additional effects. These are things I'm not going to talk about much, but we get ionization from the X-rays and the EUV, which can play a role. You can enhance the cosmic ray flux both within the cluster and within the cloud, and I'll say a few words about that in a minute. Supernova can cause a lot of destruction of the local environment. They can also provide short-lived radioactive species, which I'll say a minute about. There's another effect that as the disks orbit through the cluster, they can hoover up additional material. This is predicted to be a modest effect, although there's a recent paper I understand that says otherwise. And you can also, if you're in a dense enough environment, affect binary orbits and such. So let me say just a little bit about the particle part of this. So you could do an analogous calculation to what we did with radiation, where you take clusters, you sample the clusters, you sample the IMF, and then you use the stars that you get from that IMF sample to produce radioactive species from their explosions. And we'll assume that all the explosions happen in the middle of the cluster where the big stars are. Then you can sample all the positions in the cluster, take a typical disk, and see how many radioactive elements are hoovered up by the disk. In other words, how much mass in radioactive elements do you get? Now, I'm just going to give you the results for aluminum-26 because that's the most important one. And what you find is that you get a probability distribution for your enrichment. And the enrichment level is measured in picosons, which is kind of a nice unit. Now, that probably also doesn't mean much to you, right? What the heck is a picoson? And why does it matter? Well, our own solar system is apparently enriched in aluminum-26 above what you expect from the background galaxy. And its enrichment level is such that it's about 100 to 200 picosons. In other words, if you want to enrich our solar system to explain the observed daughter products of radioactivity seen in meteorites, you need 100 to 200 picosons of radioactive aluminum-26 when the solar system rocks were being made into rocks. That's the statement. And then with this probability distribution you calculate, you can say, well, how often does that happen? If I have this cluster sample that I've been using and the IMF that I've been sampling and the positions of the cluster I've been sampling, how often do you get 100 picosons? And the answer is about 2% of the time. I don't know if that's good or bad. That's just what the answer is. It means that only 2% of the solar systems will be enriched at our level by the cluster stars in their own birth cluster. There are other enrichment mechanisms, but this is what you get from clusters and the direct result of it. Now, there's another thing that you can get from clusters, and that's you can get enhanced ionization from cosmic rays. The story here is as follows. When you make a star, you get a disk with it, and the disk lasts for about the same amount of time as the clusters, so we'll say 3 to 10 million years. When you have a disk and you have accretion, there's a magnetic truncation radius that marks the inner boundary of the disk. At that point, there's magnetic reconnection, which accelerates cosmic rays. The same way that stellar loops on the sun short themselves out and accelerate cosmic rays. They call them stellar energetic particles when they come from stars, not cosmic rays, but they're just cosmic rays that come from stars. So every young star in a cluster will actually be generating its own luminosity of cosmic rays. And we think, for various reasons, that the cosmic ray luminosity is about 1/10 of the X-ray luminosity, and the X-ray luminosity is observed to be about 1,000th of the photon luminosity. So for each photon, Erg photon luminosity you get in a cluster, you get 10,000 times less luminosity in cosmic rays. So each star in a cluster will be generating these cosmic rays. So in a recent calculation that Marco Fetuzzo was doing, we built a grid or a mesh that describes the propagation of these cosmic rays. So each star has a magnetic field, which connects up to the other magnetic fields on the other stars. And then sort of the minimum spanning set of triangles is called the Dulany mesh. And you can calculate the Dulany mesh for a given cluster and say that each star generates this luminosity cosmic rays, which have to follow the field lines. So they will random walk themselves around the cluster and then out. And since they have to random walk out instead of just freely streaming out, it takes longer and there'll be an enhancement of cosmic rays. Bottom line is that you can enhance the level of cosmic rays by factors of 10 to 100 over the background galaxy. You could do that's what this slide says. You could do the same thing on the scale of molecular clouds, and you can get a similar enhancement. Here, the argument is that supernova also produce cosmic rays, but supernova happen to happen in molecular clouds. But the molecular clouds are supported by magnetic fields, and the magnetic fields guide the propagation of the cosmic rays. So they have to diffuse out. That gives you an enhancement. So you can get moderate enhancements of cosmic rays, both on the scale of the cluster and on the scale of the cloud. So I've come to the end of the first half of the talk, only 40 minutes in, so we're not too bad on time. And what I'd like to argue to you is that if you ask the question, what do clusters do to solar systems? They have moderate effects. They don't completely dominate the structure of the solar systems that form in them, but they have enough effect that you might want to take them into account. What do? Well, dynamical interactions will truncate disks at 300 AU, as we said. Disk will be truncated at something like 30 or 40 AU due to radiation. We see that planetary orbits are altered. You'll increase eccentricity and inclination angle moderately. You very rarely will actually eject a planet. We only expect a few planetary ejections per cluster. We can also see there'll be an enrichment of radioactive species over what the background galaxy has. It's relatively rare to get the full enrichment we see in our solar system, namely of 100 picosons. That only happens a couple % of the time, but overall you'll get more often you'll get a more modest enhancement. And finally, we see that there's cosmic ray ionization enhancements, or cosmic ray flux enhancements would lead to ionization enhancements at the order of factors of 10 or so. The other thing I want to emphasize to you that each time you ask a question, what is the likelihood that the eccentricity of Jupiter will be excited? You have to answer in terms of probability distributions. But the machinery that I've gone through here, even though I've gone through rather rapidly, gives you a way to present those probability distributions. So we have the answer. It's just that the answer is a probability distribution, and it takes lots of words to say what it is. Okay. So the first half of the talk, which is now over, I can defend. I think I did my best to do a rigorous calculation of all these probability distributions. And what I'm going to do now is one step more fun and one step less rigorous. We're going to ask the question, after 4.5 billion years, what, if anything, can we say about the birth cluster that our own solar system formed in? So what we're doing here is we're playing CSI solar system, right? We're looking for clues that were laid down 4.5 billion years ago. Remember, the clusters only live for 10 to 100 million years at most, and the solar system is old. So it's kind of amazing. You can say anything, right? So what can we do? Well, we know a lot about the solar system. In fact, we know too much about the solar system to explain all of its properties. But some of the things we know is that, as I said earlier, the solar system was enriched in radioactive elements, right? Now, that's a low probability event, but we want to look one step closer to see what the probability distribution is for our own particular suite of enriched radioactive nuclei. The other thing we see about our solar system is that the planetary orbits, namely the giant planets, are relatively well ordered. And they're relatively flat. They're all in the same plane to pretty good approximation. And what that means is that the solar system was not overly dynamically excited. It was not disrupted greatly. We also see a couple edges to the solar system. We see that the gaseousness, if you reconstruct the solar system gaseous, it goes out to about 30 AU, and then there's a big drop off. Then there's Kuiper belt objects from 30 AU up to 48 AU, it turns out. And then there's another big drop off. So there's two edges of the solar system. And then we also see things like the dwarf planet Sedna, which are excited to high eccentricity and high perihelion. And one way to get them is through scattering interactions. So by putting all these pieces together, I can give you a picture, or at least a constraint, on what our birth cluster looked like. And that's what I'm going to try to do for the next few minutes here. So first of all, let's talk about radioactive species. It turns out there's not just aluminum-26, there's a whole bunch of them. All of them are listed here. There's one important complication. That is that beryllium 7 and 10, cannot be made by supernovae, but has to be made by spallation. Iron 60 cannot be made by spallation. It has to be made by supernovae, or at least some stellar process. So we got a problem, or at least a complication right from the beginning. You can't explain all of the elements, the radioactive elements, with one source, because some are only spallation and some are only stellar. Okay, so what I'm going to do is I'm going to assume that the beryllium and the spallation sources are produced by the cosmic rays generated at the X point, like I talked about moments ago. And I'm going to assume that the other elements are produced by a supernova. And if you do that, the preferred mass of the supernova to get you the right suite of radioactive elements turns out to be a 25 solar mass star. And a 25 solar mass star is actually kind of rare, as you guys know. It's not just a star that blows up. It's not just a 10 solar mass star. It's even bigger. It's got to be 25. So it's already going to be a rare event. Okay. And that pushes us to being in a big cluster, because the bigger the cluster, the more stars there are. When you sample the IMF, the more likely you are to have a 25 solar mass star. So it turns out the probability of a supernova is 1 minus the probability of not having a supernova. And you take that to the bank. And the reason why you write it this way is you actually know F naught, the fraction that you don't have a supernova. And that gives you a nice little formula for the supernova enrichment probability as a function of cluster mass size n, where this F value is calculated based on a standard IMF. If you change the IMF, you change F accordingly, but it's the same formula. Now, we also see a well-ordered solar system. Like I said before, our giant planets have nice, nearly circular orbits, all nearly in the same plane. Specifically, these are the eccentricities and these are the inclination angles, and they're small. But we also know how to do dynamical scattering from the cross sections that I showed you and the millions of simulations that my colleagues have done for us. So we can calculate the cross section for disrupting the solar system beyond recognition. Now, beyond recognition just means enough different from our solar system that it's not our solar system. And what I mean by that is I'm going to imagine calculating the cross section for doubling the eccentricities of the giant planets and or doubling the inclination spread. Now, nothing particularly catastrophic would happen if our eccentricities were that big, but it wouldn't be our solar system, so we know it didn't happen unless you go out there with a spaceship and steer them back into the right orbit. So in the absence of some extra mechanism, we just know that didn't happen. And the cross-section for that turns out to be 400 AU quantity squared, which you'll recognize is actually quite a bit bigger than 30 AU squared, which is the actual geometric size of the solar system. And specifically, that's the cross-section you need to get the eccentricities bigger than 0.1 and or the spread in inclination angles bigger than 3.5 degrees. So you put all these pieces together and you say, I want to have a cluster that's big enough that I get supernova enrichment and small enough that I don't mess up the planetary orbits. And I put those two probabilities on the same plot, there's two probability distributions on the same plot, and multiply them together so I get the joint probability of both of them happening. You see you get a nice peak with a little bit of width, and you see that the expectation value for the birth size of the cluster is a couple thousand stars. Specifically, from that particular set, you get 2,000 plus or minus 1,000. If you then take that probability distribution of having both effects and integrate over what you think the cluster distribution is, you get a 1 in 60 chance. In other words, 1 out of 60 solar systems will be enriched at the level that our solar system is, but not dynamically disrupted any more than our solar system. Now, that's actually not a bad number. 1 in 60 events happen about 1 out of 60 times, as it turns out. And you would worry if this were 1 in a billion or something, but it's not. It happens often enough that it's fine, right? And there's nothing particularly important about the solar system planetary orbits having low eccentricity or as low as they do, only that they do, and we could use that as a clue to what our dynamical history was. But we can put on more constraints, and we want to see whether they mess up this picture or not. So one thing you can do is say, well, suppose I want to make Sedna. So Sedna is this crazy Kuiper belt object that has very unusual orbital elements, an eccentricity of 0.82 and a periastron of 70 AU, so it's way the heck out there. It turns out you can make Sedna if you make a close approach. And the closest approach you need has to be in the range from 400 to 800 AU. Now, that's actually kind of reasonable. We saw that the typical closest approach was going to be about 1,000 AU. So every once in a while, you'll get one at 800 or 500, and that's good. And you want it to be at 500, not at 200. Because if it's 500, you can make Sedna and not mess up Neptune. But if you make it a lot closer, you'll jostle the giant planets, right? So we want to put that constraint on our picture. But we also want to look at the radiation content. We saw that radiation was the most important thing that clusters do to their solar systems. And if you have too big a cluster, you have too much radiation, or too high a probability of having too much radiation. And you could evaporate the solar system down past Neptune so that we don't make the giant planets as readily. When we put these two constraints on that same plot, you get this plot. So I now have 4 constraints. The dotted line is the radiation constraint, which is almost kind of sort of the same as the constraint that I do not have too much dynamical disruption. The solid curve was the supernova curve I showed you before. This dashed curve here is the probability distribution for getting a closest approach close enough to give you Sedna, which is very much very close, it turns out, to the supernova constraint. So if I put all these things together, I get a revised version of my probability distribution, which has a expectation value of about 4,000 with some width to it. So that's perfectly reasonable. So if you believe all of this, the picture that emerges is that the current day properties of our solar system give us an estimate or a set of constraints that tell us something about the birth environment of the solar system. It's a cluster size that if you use the full size, its range is from 1,000 to maybe 7,000. If you integrate that probability distribution under the multiplied or convolved with the probability distribution for cluster sizes, you get the a priori total probability of a few percent, which means a few percent of solar systems will have these 4 crazy properties that our solar system does, which is perfectly reasonable. This allows the meteoritic enrichment we see and the survival of the giant planet orbits. It allows the production of Sedna and the survival of the disk down to 30 AU. So we can explain all of these. As a bonus, if you produce Sedna with the scattering interaction, you also truncate the Kuiper belt at about 50 AU, which we also happen to see. That doesn't mean that's why we see it, but it does provide a possible explanation, and it is in fact consistent. So we have a pretty good story, but you'll immediately start thinking about problems with my story. So let me anticipate these and give you some of the problems that you're about to think about, okay? So the first is that if you want the supernova to actually enrich the solar system, you have to be a little bit lucky, and you have to be kind of close to the supernova blast in order to get enough radioactive nuclei. Turns out you want to be within a couple tenths of a parsec. Now, the whole cluster is only about a parsec in radius, so you have a 1 in 5, 1 in 10 chance of doing that. That's not a problem. But you can't be too close either, otherwise you'll destroy the disk. So there's a window. It's not super narrow, but it's not super wide either. There's a moderate window where you have enough enrichment and disk survival. So that's possible, but it's another constraint on the story. And if you start thinking about this, there's other constraints. We want, or we're invoking, a 25 solar mass star. And a 25 solar mass star lives for a main sequence lifetime of about 7.5 million years. Now, that's not a big problem because the clusters typically live for 10 million years, and the disks live for 3 to 10 million years. But in order to enrich the disk and have the supernova go off to enrich the disk has to live kind of on the long side. Not crazy on the long side. 1 in 10 live 10 million years, so that's not a problem. But you got to be a little bit lucky in that regard, right? You also have to be lucky to have a close encounter that's close enough to produce Sedna, close enough to truncate the Kuiper belt, but not close enough to mess up the giant planet orbits. So you got to be a little bit lucky there. And in order for all these things to play out best, it works better if the solar system lives in its cluster for a little bit longer than average, which is also possible, but it's not guaranteed. And finally, the Oort cloud has to happen later, which is also not a problem, but it's another constraint on the system. If you have an Oort cloud as big as the Oort cloud inside a cluster, it will be stripped. So if you want our solar system to have an Oort cloud, and we think it does, the Oort cloud has to be produced after the solar system leaves this birth cluster. So all of these things are quite possible, but none of them are guaranteed. So the picture that emerges is that in order for our solar system to be our solar system, a lot of things have to go right. Okay, now think about what that means. Like just for the supernova enrichment, we want to be close enough to the center that we get enrichment, but far enough away that the disk survives. Let's say that's a 10% effect. 10% effects, no problem. 1 in 10 happens, right? But we also need to be those, we also need all those other things that I described to happen too. We have to have a lucky close approach, but not too close. All of these things are kind of at the 10% level, but guess what? If you have 10 things that you require at the 10% level, all of a sudden your probability is 1 in a billion or 1 in 10 billion, right? Is this a problem? Well, I don't actually think so. I thought about this a lot, or at least a little. What this means is that there are more ways to make a solar system than we have solar systems in the galaxy. You have this long combination of things that happen: a certain mass, a certain orbit, a certain edge, a certain sedna, a certain radioactive enrichment. If you want everything to be exactly like our solar system, it's going to be a 1 in a billion chance, right? But guess what? If I want everything to be the same as you and your DNA, what are the chances of that? It's much less chance, much smaller probability than 1 in a billion. But you're here sitting in front of me. How did that possibly happen? Well, it's not a problem because you're choosing the probability after the fact. After you have a multivariable problem like choosing Chris's DNA or choosing the properties of our solar system, it's a rare event, but it's already happened. So it's not the probability it will happen. It's just that there's that many combinations. There are more ways to make people than we have people on the planet. There are more ways to make solar systems than we have solar systems in the galaxy. And that's kind of an interesting perspective that I should not dwell on any further. So I want to come clean. There's another problem, is that you can enrich radioactive species in different ways. You can enrich them with the X-Wind models, so we think we might need for spallation. You can enrich them with AGB stars, which is problematic because the AGB stars wander far from the birth environments. The nice thing about supernovae is they're close to the birth environments, but you have to be a little bit lucky to get AGB stars or Wolf-Rayet stars to do the enrichment. A more promising avenue is to do a distributed enrichment scenario where you have not one supernova, but a bunch of supernova in a big massive star environment. And that will make lots of basically chaos, but lots of enrichment in the local environment. And then subsequent generations of stars that happen not too long afterwards can be enriched. And that will also work or can be made to work. The other thing that I think is problematic and yet to be worked out is that you do need a spallation source and you do need a stellar source. You can't explain the iron 60 with spallation, and you can't explain the beryllium with stellar processes. So one way or another, you're going to have a joint result. So I'm running out of time. Let's go back to our original questions. The original questions, as you remember, are that we asked, how does the initial cluster, or how does a cluster initial conditions affect solar systems forming within it? And the second question was, what, if anything, can we say about the basic properties of our birth cluster? So the answer to the first question is that I've given you distributions to the answers to all of the things, not all of the things, a collection of things that the clusters can do. We have distributions of closest approaches. We have distributions of FUV and EUV and X-ray radiation. We have disk evaporation models that tell you how much evaporation you get for a given FUV flux and also for a given EUV flux. We've calculated cross sections for solar system disruption, capture, and other things. We've calculated distributions of supernova enrichment of short-lived radioactive elements and other things. And all of these things you can take to the bank. We have the probability distributions. And then for the other one, we can say that the birth environment of the solar system is likely to be a cluster with stellar membership size about 4,000 plus or minus 2,000. Now, if you want to be conservative, you can widen that result to be the decade from 3,000 to 10,000 stars, but that tells us kind of where we are in parameter space. And you could explain a number of properties of the solar system if we in fact formed in a cluster in this size range. And it's not too different. This is kind of what the ONC and Orion is. So you can see one of these with, at least with binoculars. Maybe those young ones with good eyes could see it without binoculars, but you don't have to go so far to see such a cluster. So let me just say that I'm right on time ending. There's this number of papers that all give you all the details. So I've probably spent too much of my career writing all these papers, but for those of you who want more details, you can take a look. So I'll leave my conclusions up and I will take questions. So thank you for your patience.
Do you think there are epochs in a cluster's life where it is more conducive to form planets? It's like at the when the cluster is born or when the cluster is about to disrupt or somewhere at the midpoint?
I would say not really. And what I mean by that is that my understanding of clusters, and some observers can correct me, is that the typical, well, 90% of stars form in clusters, which I'll call young embedded clusters, which live for 10, 20 million years. Only 10% live in long-lived things that will be the Pleiades and open clusters. So in the 90% that live in the young clusters, as far as we can tell, and it's notoriously difficult to tell, the spread in star formation times is relatively short. It's only a million years or two. It's consistent with 0, but because the error bar is big, but it's only a small fraction of the small lifetime. So the picture that emerges is that you form most of your stars in, let's say, a million years or two. The gas goes away in another couple million years, and then you have the time when you have disks, planet formation, and whatever disruption that my talk addressed. But you don't have multiple epochs in the typical cluster. In a globular cluster, you can have different generations of stars and such, but they live much longer than what we're talking about here. In the typical embedded cluster, you kind of only get one shot. I mean, there could be slight complications, but to 0th order, that's my answer.
Thank you. So you did a good job of anticipating the question I was going to ask about the radioactive nuclides and the fact that it takes time to have a supernova and the disks are gone by then. So,
well, not always, just sometimes.
Yeah. So do you have an idea of the numbers of comparing how likely it is to get, how many stars would have this kind of enrichment, if the sun was born a tenth of a parsec from a supernova versus if it was born in the second generation that gets blasted by a bunch of supernovae and absorbs the ejecta more efficiently? Like, wouldn't a larger fraction of stars have the enrichment in the second case?
Well, people are still trying to do that calculation, and they do not agree. I think both scenarios are still on the table. So it's to be determined. It's a good question, but I don't think we have a definitive answer. I think both work at the moment, but I don't know that we have a definitive description of the probability of each of them. And we'll never have a definitive answer. We'll only have, well, this has this probability of working and this has this probability of working. What I presented here is that the probability of the supernova in the cluster enrichment scenario is not crazy small, so it's still on the table. I don't think anyone's done the analogous thing for the distributed enrichment. They've only demonstrated that distributed enrichment does in fact work.
Thank you so much for that incredibly stimulating talk. I had a lot of fun. So my question is, I'm wondering if you've thought about how the larger galactic environment affects the planet, the fraction of planets in a system, or and how does it fit into this context?
Oh, that's a good question. It depends a little bit on what you mean. The way I envision things, and this might be a theorist being too naive, is that star formation takes place on the scale of molecular clouds. So once you're on a scale bigger than that of a molecular cloud, there's relatively little that matters because the molecular cloud shields a lot of the background radiation. It's also very dense and kind of decoupled from the galaxy. The one thing the background galactic background does is it provides a metallicity gradient, and metallicity will play a role at some level. So the inner part of the galaxy is more metal rich and the outer part of the galaxy is more metal poor. So metallicity will play a role. I don't know if you count that as a background effect of the galaxy or just an additional condition of the cloud that has low metal or high metal. The one exception to what I'm talking about is you go to the very galactic center where things are really intense. the molecular clouds are really dense, the magnetic fields are much bigger than average. There's a tendency or a hint, and I'm not exactly sure what the current observational status is, but there's claims of more top-heavy IMF there. There's lots of B stars we see. So the top-heavy is B stars, not 10 to the 6 solar mass stars. But there's a little bit of hit in the extreme environments like the very center of the galaxy, where what I'm saying might not be true. That's all I know about that, though. So.
I had a question about the sort of constraint on a close enough but not too close stellar flyby to explain the orbits of Neptune and Sedna. Is there good reason to believe that Sedna's orbit would be described better by a stellar flyby than just planet scattering that might be more common anyways, a near ejection sort of planet scattering?
The short answer is yes. It works better to have a flyby to explain it. Scattering of things from the giant planets tend to work if the periastron is just outside that of Neptune. The weird thing about Sedna and a few other things that we call sednoids is that they have periastron that's much bigger than Neptune's orbit. And once you're outside the realm of the influence of Neptune, how do you get more pushing on it to get it even further? If you know, let me know. We'll write a paper. But I don't think we know. And that's why people have invoked flybys. Now, that doesn't mean flybys are the answer. It just means it's the best one that people have come up with. So you might have your own solution, right? Which would be great.